everyone, this is Dr. Zach. I'm so glad that you're joining me today. For today's lesson, we're going to talk about tangent line approximations, differentials, and propagated error. Propagated error is used in scientific research, so this should be quite helpful to you. For today's lesson preview, you are reminded of how to write the equation of a tangent line at a given point. So the answer you should have come up with is y minus 1/2 equals the square root of 3 over 2 multiplied by x minus pi over 3. So if you didn't come up with that answer, please go back, review your notes, and then ask questions if necessary. So the purpose of question B was to remind you that the AP expects you to round your answers to 3 decimal places, and also to show you that when you substitute the 1 into your equation for the tangent line, your answer is incredibly close to when you substitute into the function itself. And we're going to discuss why these answers are so close. The equation of a tangent line is used for linear approximation. You know that you have y minus y1 equals m times x minus x1. Well, y1 is your function evaluated at a. F prime at a is the slope at that point. Now, when we look at the graph of the curve, you can see that the tangent line just touches that one point. And if you were to choose a point that you're interested on the curve, perhaps you wouldn't be able to evaluate it using the actual function. So what we'll do is take that number or value for x and substitute it in for x on the equation of the tangent line. The answer is not perfect, but you can see that it's very, very close. So that piece that it's not quite right, that's going to be your delta y, or your f of x plus delta x minus f of x. dy is going to be equal to the derivative multiplied by dx. And also what you can tell from this graphic is that dx is equal to your delta x. So using the equation of a tangent line gives you a great approximation for the value of the function at that point. Now, the further that you get away from your tangent point, the worse your answer is going to be, because your delta y will be larger. For our first example, we're told that f is a differentiable function and that f of x is, f at 2 is equal to 6. So we have a point. And that f prime at 2 is equal to negative 1/2. We're asked to approximate the value of the function. Now, it's an approximation because we cannot find the exact value. To do that, we're going to take y minus y1 equals m times x minus x1 and write the equation of your tangent line. So we have y minus 6 equals negative 1/2 because the slope is the derivative at 2 times x minus your 2. So y equals negative 1/2. I wouldn't multiply through, just keep the negative 1/2 in front of your parentheses. And you have your x minus 2 plus 6. Now we're asked to approximate the value of f of 2.1. So f of 2.1 is approximately, so we use the symbol for approximately, negative 1/2 times 2.1 minus 2 plus 6. You can see it helped just a little bit not to distribute that 1/2. And when you simplify your problem, you will get 5 and 19/20. Now these are not calculator problems, so please do not practice this type of problem using your calculator. Note the notation once again. When we substituted in our 2.5, instead of an equal sign, we were using an approximation because we are approximating the function at the point 2.1. So as you work on number 1, The directions say use the tangent line to find the approximate values. So write your equation for the tangent line before you do anything else. And remember, the slope is the derivative evaluated at a point. You should never put in a variable expression. So I'm specifically looking for f prime at 2, and that should be a number. Example 2 involves a trig function because I know that you love your trig so much. So as we look at example 2, notice I didn't name f of x. I didn't tell you to write the equation of a tangent line. You have to understand that when you're approximating a value, that the equation of the tangent line is your go-to tool. So let's define f of x to be equal to the sine of x. Now, 29 degrees is close to 30 degrees. So we should write the equation of the tangent line at 30 degrees. And we know that f of 30 degrees is equal to 1/2. When we find the derivative, f prime of x is going to be equal to your cosine of x, and the f prime of 30 degrees, which is your slope, is going to be the cosine of 30 degrees, and that, of course, is √3/2. So now you have your point and you have your slope. You're ready to write your equation. Y minus your y1 is equal to m times x minus x1. We get y minus our y value is 1/2 equals the slope, which is the derivative at 30 degrees. So that's √3/2 times x minus 30 degrees. All right, so what you should notice is this little piece here says x minus 30 degrees. Subtracting 30 degrees is not going to be the same units as when you're working with 1/2 and √3/2. So we need to change our problem into radian. And to change the problem into radian, we're going to have to multiply by a pi over 180 degrees. So our equation is y equals √3/2 times x minus 30 degrees. That will be multiplied by pi over 180. Notice the 180 degrees will cancel out the units degrees, and then we have our plus 1/2. Specifically, we're interested in f at 29 degrees. So that's going to be approximately equal to your √3/2 times 29 minus 30, those are degrees, times pi over 180 plus 1/2, which is going to be equal to √3/2 times negative pi over 180 plus 1/2. Now you don't have to get too worked up about simplifying. So if you want to write 1/2 minus √3/2 times your pi over 180, that will be just fine. You are going to work on questions 2 and 3 yourself. For question 2, you might want to establish that f of x equals x to the 1/2 power before you begin. For question 3, make certain you read your directions. The directions say that the slope of a function is given by the negative x plus 1 over y. So given that piece of information, you should be able to find your derivative at 3 and answer the question. So it's time to look at that graphic a bit more closely. We have our function f of x. And from f of x, we've drawn a tangent line. So this tangent line is meeting at the point CF of C. Now, the different pieces, we talked briefly about them in the last graphic. dy is called a differential of y. And dy is equal to the derivative multiplied by f of x. Notice that dy is the length of the line that I'm drawing in blue. Delta y is the difference of f of x plus delta x minus f of x. So your delta y is going to be the part that I'm drawing in red. So you can see that delta y is approximately equal to dy, your differential. And if that's true, then your delta y is approximately equal to f prime of x dx. Now, dx is called the differential of x. But as we look at the picture, dx and delta x are the same thing. So your differentials are used to measure the amount of error that can occur. Now, this error occurs when you're using a ruler, a micrometer, scales, polling instruments, or even measuring cups. You will never get precise measurement, and we need to understand the error. Let's look specifically at differentials. So we know that delta y is f of x plus delta x minus your f of x. And delta x is a measurement error. dy is approximately equal to delta y, and this is called the propagated error, or error due to measurement. X plus delta x is an exact value, and x is the measured value. Now, relative error is defined to be your dy over y. So that would be your propagated error divided by your actual measure. The percent error is, of course, taking that ratio and multiplying it by 100. So this is used whenever you are measuring some sort of object and then using that measurement within other equations. So we've measured the radius of a pellet in the shape of a sphere to be approximately 5 millimeters. Your micrometer has an error of plus or minus 0.01 millimeters. So the error was given to you as part of your measuring instrument. We're going to use differentials to estimate the propagated error when calculating the volume of our sphere. And then we're going to figure out the percent error as well, just to complete this problem. So we start with the volume formula. We have volume equals 4/3 pi r cubed for a sphere. We're going to find the differential. dV equals your 4 pi r squared dr, a little bit like implicit differentiation. We know that r, the radius that we measured, was 5 millimeters, and that the instrument we are using to measure is going to be off by plus or minus 0.01 millimeters. So to find the error, we need to think about dV. dV, through substitution, is 4 pi times 5 squared dr, which would be the measure of error from your measuring instrument. So in this problem, we're going to get plus or minus pi millimeters. Now think about it, it's going to be millimeters cubed, because when you are working this out, you've got r squared times dr, which means r cubed, or radius cubed. All right, so we have the propagated error. From that, we find our relative error, dV divided by V. Well, that's going to be your pi r squared dr divided by your, 4 pi r squared dr divided by your 4/3 pi r cubed. When you simplify, you end up with 3 over r dr, or 3 over 5 times plus or minus 0.01. That gives us 3 over 500 plus or minus the error. The percent error then is going to be 3 over 5% error plus or minus. All right, so if you use this measuring instrument and then substitute your answers into a volume equation, the percent error for the calculation that occurred is plus or minus 3/5%. Often in this course, you're just asked to find a differential, which means find dy. So dy would be the derivative of your cosecant 2x, which is going to be -2, cosecant 2x times your cotangent 2x times dx, and that would be your differential dy. Now, when you're asked to compare delta y and dy, you want to perform two separate measurements. Delta y is f of x plus delta x minus f of x. So in this problem, that's going to be f of 1.1 minus f of 1, which works out to be -0.42. dy is the differential of y. That will equal -4x dx. So when we substitute, that gives us -4 times 1 times 0.1, and that is -0.4. So the difference between your delta y and your dy is going to be 0.02. That is your difference. So now it's time for you to practice working with some of these concepts and definitions. Problems 4 through 8 provide an excellent opportunity to see if you understood what we were working on. Give these a try, stop the video first, and then once you've attempted each question, I will present a few of the answers for you. Stop the video now, please. So today's lesson follow-up can be found on the worksheet. The questions from the book have been placed on the worksheet as well. Thank you for all your work, and you have a great day.